I would like to talk about two things. Well, firstly, I would like to finish what we started last week, namely the Dolbeau complex, and there was there were a few items which we didn't manage to really understand. So let's start by by doing this, and then it's time to talk a little about sublove spaces. But before we move on to these topics, there is no single day or time which suits everyone for the extra classes. So, every day of the week, including Saturday, is inconvenient for at least one person. So we'll probably have to make a choice. I suggest we have a vote, not now, but by email. And basically, the idea is to have a class on Friday, Saturday, or Thursday. So it's not to have two classes, one after another. Well, probably Saturday is convenient to everyone except Yegor. Saturday is not convenient. Yes, well, Saturday afternoon, after 3. Okay. Did you mention this in the table? Yes. So one thing we could do is have a class on Saturday, and then I'll record. We could have it on Zoom, and then I'll just post the recording on the YouTube channel, or somebody else will. Yegor, what do you think? Ну, значит, относительно, то есть, ну, я бы сказал, где-то, ну вот, Володя говорит, что с 3, ну, то можно где-то с 3 до, там, я не знаю, там с 3 до 7, вот, насчет такого сорта. Или там. Ну, да, и в любом случае, это, значит, это все я планирую сделать в Zoom. Да. Well, that's the plan anyway. Okay. Well, I'll send an email, and we'll have a vote. Okay, now let's remember where we got stuck last week. We want to understand the cell duality for holomorphic vector bundles. And to do this, we constructed well, first of all, we constructed the star operator. Well, let's start with the star operator, which acts on differential forms. The star operator was obtained as follows. We first complexified the differential forms, and then we take a Hermitian metric on E, and we use this metric to build the star operator, and then we take the composite of the complex conjugation and the star operator obtained using the real part of the Hermitian form. And we proved that this, or at least sketched a proof that this operator takes sections of this bundle to sections of this bundle. Or actually, even this operator is of order 0, so it's just a map of vector bundles. So actually, it's a very simple kind of operator. And now we want to we want to oh, by the way, here I need a Hermitian metric both on the tangent bundle and on E. So. And once I have a metric on the tangent bundle, I also have one on the cotangent bundle. Okay, now does this make sense to everyone? or sort of, or not at all. Well, let's see. We want to prove that this star operator commutes up to some multiplication with the Dolbeau operator, and I mentioned this last week, and then I got confused, and basically this was it. First of all, let's complexify the de Rham operator, and we get an operator which this time will be of order 1, and which will take sections of lambda something to sections of lambda something plus 1. Okay, now let's complexify the de Rham operator and call the result also D, using the same symbol. Now, we know from one of the previous classes that the star operator almost commutes with D, and so the where this epsilon okay, this this epsilon to begin with, epsilon is just some non-zero number, a real number. Then we get the same identity for complexifications, and then I want to prove the same identity for. Oh, sorry, no, this is wrong. I need to put a big D, where D is D plus D conjugate. Okay, now let me put a D here to show that this this operator corresponds to the de Rham differential. Now I want to prove the same formula for the de Rham for the de Rham differential. No, sorry, for the Dolbeault operator, which is d bar plus d bar conjugate. Okay, now does any of this make sense? Well, it's some number, plus 1 or minus 1. Yes. Okay, now let's see. So one of the reasons it didn't work last time is that I started thinking about the Laplacian operators, and the Laplacian operators for D and for D bar in general are not the same. And by the way, does anyone know when those Laplacian operators are in fact the same? Yes, it's one of the ways to reformulate the condition that x is scalar, or more precisely, the metric on x is scalar. And so, in particular, if we take the Fubini-Studi metric on a projective variety or a smooth projective variety, we do get two Laplacians which are in fact the same up to some factor. But in general, the two Laplacians have nothing to do with each other. Well, they have something to do, but they're not the same. Okay. Now, let's not worry about the Laplacians. Let's just consider the operators themselves. Okay, now okay, does this expression make any sense? Say again?
I mean, what are these, how to say, like this D operator, small d?
This one?
This, yes.
No. Okay, let's try to remember. We have the complexified drum operator, which would denote D. And we so this operator goes from sections of this bundle to sections of this bundle, and then we write it as d plus d bar, where d bar is the vertical component and d is the horizontal component. Now this goes from PQ to PQ plus 1, and this goes from PQ to P plus 1 Q. Okay, so what do? We decompose this space into, well, let me put an n here. No, not n, m. Now we decompose this as the sum of lambda PQs, and then we just separate, look at what happens for each individual PQ, and then we declare the horizontal component to be D and the vertical D bar. And both D and D bar square to 0, and this is one of the ways to rephrase the fact that the complex structure is integrable. Okay, now okay, does anyone understand how to deduce this identity from this identity?
So we just write D is D.
Well, this identity would follow if if the left-hand side of this identity would be some component of the right-hand side of the left-hand side of this identity, and same for the right-hand sides.
So we just say that we introduce operator d without bar.
Okay, so d is d plus.
No, wait. We don't have. Yes. Then d is a d plus d bar.
Well, there's one thing one needs to be careful about. So, is it true that G star is delta star plus? Okay, normally people say D. But those D's are different. So anyway, is it true that we have this identity?
Yes, because star is linear.
Well,
No, that's star.
yes. So the yes. So the operation of taking the conjugate is the conjugate operator is linear in the sense that it's R linear. And it's not linear over C, but anyway. So Yegor, what do you think? Is this formula true, or is it some kind of a deception? Well, Leonid says that taking the conjugate operator is is at least R linear. So we have this. Yeah. So let's see. So here we have there's one potential problem. We have okay. So this D is decomplexified. So this is the complexification of the de Rham operator. Now we prove this formula for we prove this formula for the real de Rham operator. So let's see how complexifying interacts with taking the conjugate. In other words,
ПК формы, соответственно, там, ну, там у нас их не появится, в общем.
Сейчас,
У нас P Q плюс 1 формы могут отправиться оператором D в P минус 1 Q плюс 1 форму. Извините, что по-русски, но по-английски я буду просто совсем.
так, значит, еще раз. Значит, какие формы в какие формы?
Ну, D отправляет PQ, P плюс 1Q, прямая сумма с P и Q плюс 1.
Так, да.
Когда мы к этому применяем D сопряженное, оно куда отправится? Оно может отправиться в P.
Сейчас, а зачем мы применяем к этому доспряженное? Мы применяем...
Мы же сопряженное оператор к чему применяем? В каком пространстве будет D со звездочкой?
Значит, да, значит, D у нас просто прямую сумму всех ПК переводит в прямую сумму, значит, ПК, но с, значит, P плюс Q там на единицу больше.
By the way, which metric do we use to conjugate D?
Well, we say that we take some Hermitian metric on M.
Okay, we take Hermitian metric for M, but when we take a conjugate operator to the RAM operator, we need just Riemann metric.
Yes. The real part of the real part of the Hermitian metric is a Riemannian metric, and we use this one. Okay. Now let's see. So we have. We have we have a map of Euclidean spaces, and we in which, in our case, these will be the spaces of differential forms. Now. Okay, let me. Let me consider a map of Hermitian metric of Hermitian spaces. And then the which means we have a complex structure on these spaces, but we forget it, and the map we consider is just a map of real vector spaces. But we use a Hermitian metric to to define the conjugate, which is what we do with differential forms. Okay, now let me complexify this map. The left hand and the right hand side of this map are this time complex vector spaces and these have the decomposition into the space plus the complex conjugate. Now, if we have a Hermitian metric on V1, we have one on V1 plus V1 conjugate, and same for V2. Now. Is it true that the conjugate of the complexification is the complexification of the conjugate? Let's think. So both these are Hermitian. So what do you think? Both are maps from this space to this space. Well, let's imagine for a second, or pretend that those spaces are finite dimensional. In which case, this is just linear algebra. So.
Is it true that we can recover Hermitian metric from its real part?
Well, no, not in general, because well, the complex part could be basically any anti-symmetric form on the same real vector space. Basically, to have a Hermitian metric, we need to have a Euclidean metric on the underlying real space, plus a non-degenerate anti-symmetric form on the same real vector space.
So then the left part doesn't know anything about this subjective form. But the right hand side depends on the
the right hand side. Let's see. Well, no, the right hand side is the conjugate of A, but to calculate the conjugate, we only use the real part. Okay. I suggest we'll think about it, and in the meantime, I'll go and get some water. So, what do you think?
This second component must be negative. It acts on the real and the complex part must be negative.
What does it mean? The second component is negative.
I mean, because when the complex pi operator, it acts on the real part and the complex part. And after the adjunct, the complex part would be negative of the real part would be the same.
What does it mean that that it's negative? Okay.
For example, if A acts on just real vectors like V, so just gonna write this as the complexified. It acts on V2, and this is the representative of the complex.
Sorry, what does this mean? V1, V2?
I mean just this. So by definition, it's just
Yes.
So when we complexify this and then the adjoint and the adjoint of must be so it will be negative.
Okay, and why do we have this formula?
Just we have to write like this. I mean, just by definition. And if we open this by definition of this and just use the Hermitian property, should I?
I don't know. What do you think? Does everyone agree, disagree, or neither with Saman?
How did you get that formula?
This?
No.
This?
Yes.
This? Oh, but okay, then
You can erase anything. Okay. Well, so what's the relation between these two operators? Are they the same? Are they the same up to conjugation, or are they completely unrelated?
Okay, да, conjugation line.
So we take one operator and then compose it with conjugation.
Okay, so so the claim that someone is probably making is that these operators are not the same, but the same up to conjugation. Okay. So let's look at what it says here. Does this make any sense? And does it prove this this formula?
So we recover the form from its real part.
How?
So we needed to compute some. We form only two vectors. Then we just said that these two vectors are v1 plus I v2 and w1 plus I w2. Then we used made some things, and all the forms below are real parts.
Here.
If we take I to
Okay, so here, Saman, what is this thing? Is it the just the real part, or is it the what you know by
The complex pi of A.
no, the brackets? Is it the is it the Hermitian form? So the brackets the brackets here are the Hermitian form. Okay, now okay, so the okay, there's one other thing here. which we should remember. So this thing only uses the real part of the Hermitian form, because here we have a map of real vector spaces. We don't have anything to. We don't need anything else apart from a metric to construct the conjugate map. But Leonid tells us that we shouldn't forget the imaginary part. So here we have A tensor C, which is a map from a complex vector space to a complex vector space. So this conjugate only uses the real part of the Hermitian metric, but this conjugate also uses the complex part, the full Hermitian structure. Well, let's figure it out. It's not exactly rocket science. But let's just write it down. So there are two conjugations. But the operator is real, so this shouldn't be too surprising. It shouldn't be too surprising that one conjugate is determined by the other one. Okay, let's... Вот я тоже не понимаю. Давайте подумаем.
Мы же берем фактически, у нас вообще нет никакой метрики изначально, у нас Риманова только.
Ну,
у нас вещественные пространства.
Нет, сначала нет, она у нас есть на обоих комплексных пространствах, но для сопряженного оператора на первом этапе мы ее не используем. Мы используем только вещественную часть. Вот, а потом мы комплексифицируем, значит, получаем комплексное пространство. Там уже для сопряжения мы используем в смысле уже всю эрмитовую метрику. Да, значит, у нас совершенно верно. У нас есть вещественный дерам, значит, есть сопряженный к нему. Для того, чтобы построить сопряженный, нам нужна только эвклидова метрика. Больше ничего не нужно. Well, actually, it may look like we're wasting time, but this is one of the bits of the theory of complex manifolds, which is a bit tricky. So it's not a waste of time. Let's figure it out. It's not a massively difficult question. Or anyway, so Saman says that the two operators are the same up to conjugation. Up to composition with a complex conjugation. And here is, well, here is a proof. Does everyone agree?
Maybe we don't use the whole Hermitian metric because we, in the beginning we have Hermitian metric, then we forget about, we remember only real part, and then we complexify.
Yes, this is for the left-hand side. But for the right-hand side, we have already a map of the complexified spaces, so we need to use the whole Hermitian structure to define the conjugate.
Does just remaining metric induce on V1 and V2 induce Hermitian metric canonical on V1 tensor C and V2 tensor C?
Yes.
So we can just extend this Hermitian, this Riemannian matrix on V1 and V2 to complexified spaces just by linearity.
Hold on. Let's see. So. Well, there's something strange here. How do you construct a Hermitian metric on the complexified space from a Euclidean metric on the space without using bases?
Without using basis, no problem. Easy, just like that, but forget about operator. AC just.
Да, но здесь мы в другом порядке сделали. Здесь у нас было вещественное пространство, мы его комплексифицировали, там ввели метрику, а потом перешли обратно к вещественному. Там черт знает, что может делаться.
Да, я думаю, что вот в этом доказательстве мы про ту метрику, которая изначально была, про ее комплексную часть, мы забыли.
Так, значит, вот это неправильно. Мы не. Anyway, let's. Okay, so. Anyway, Well, I think this is not the metric we're after in this case. I think we need the whole Hermitian metric which we had in the beginning, and which induces a Hermitian metric on this space. So it's not just Euclidean tensor C.
There are no other metrics.
We already no. We have a Hermitian metric on spaces, on both spaces. But first we forget about it and define the conjugate operator, and then we remember and define the other conjugate operator.
But if we fix the Euclidean metric on A, then we have only one Hermitian metric on A tensor C that if we restrict it to A, we get our Euclidean metric. So any Euclidean metric can be on A can be extended to A tensor C.
Well, A tensor no. A tensor C is
not A V tensor C.
okay. So V. Okay, let's see whether or not this is true. I'll erase this part. So Leonid is saying that if we have V tensor C, we start with V, a Euclidean space. Leonid is saying that there exists a unique Hermitian metric on V tensor C, such that what?
Such that its restriction to V.
And what does it mean, restriction to V? There are several copies of V here.
Two copies. V and V.
Well, no. There are. Well, there is a map. V goes to V tensor 1,
Yeah.
which is not complex linear, but it's a map. And there are two other copies, namely the eigenvalues of the eigenspace of I, the eigenspace of minus I, such that its restriction to what?
Tensor 1.
Okay, now this is what Leonid is saying. Now, do we agree with this?
part in V tensor 1 and the V tensor I. So we can, I can write.
Well, so Leonid suggests we proceed by linearity, namely x1 plus I x2, y1 plus I y2 is well, just by linearity. Okay. Now, which looks true. What do you think? Okay. Now, coming back to our example, the Да, мы стартуем с комплексного пространства, но значит, когда мы сначала определяем сопряженную к дираму, мы пользуемся только обычной значит, эвклидовой структурой, мы не пользуемся мнимой частью. Так, насчет мнимой части мы никак не можем воспользоваться. Значит, ну, хорошо, да. Well, let's think. Does everyone agree? That there's okay. Well, let's do the following thing. Let's think for let's think for 10 more minutes, and then if we are not able to figure it out, I will. Then what does this mean? This means it's this particular bit of complex geometry is tricky. So I'll try to write it down and post the notes. It's tricky, but it's important. Why is it important? Well, because we want to prove the CR duality theorem. So okay, and as I mentioned last time, I'm not quite happy with what happens in the book by Griffiths-Harris because because everything is in coordinates, and it's well, it sort of distracts from what's happening. Anyway, let's think. So I agree with this. I agree with this statement. Now, but
Вообще есть вариант уйти на перерыв и обсудить это неформально.
Ну хорошо, да, значит, ну, у меня предложение. Давайте хотя бы еще 5 минут подумаем и потом реализуем то, что предлагает Егор. Well, let's think for 5 more minutes and then we'll try to figure it out.
Do we want to prove that statement that the dual is the dual plus the bar dual?
Sorry, which
What are we trying to prove?
we want to understand how d bar dual is related to d dual. So the optimistic conjecture is that we have this d bar dual, which takes PQ forms, which basically goes in the opposite direction. And the optimistic conjecture is that d bar dual is this component, and d dual is d conjugate is this component. But we need to prove this. So far, it's just a conjecture. Okay, let me think a little.
Так, а Риманова метрика на веществе нет, у нас просто действительная часть.
Действительно, часть Эрмитовой метрики.
Вроде вот мнимую часть можно восстановить по действительности с помощью комплексной структуры. То есть вот мнимая часть от УВ – это вещественная часть от И на В.
Ну хорошо, да. Так, сейчас. Ну хорошо, да. Так, хорошо. Ну, значит, Значит, зерам мы комплексифицируем вот в буквальном смысле, а именно тензорно умножаем на единицу в c. Ничего по-другому, никак по-другому мы комплексифицировать не можем. Поэтому здесь, здесь вот стоит вот ровно то, что нам нужно. Значит, дальше, что мы делаем с другим, дальше вопрос, у нас тут пространство, мы там хотим ввести, эрмитовую метрику. Первое, что приходит в голову, это сказать, ну хорошо, вот у нас есть метрика в самом пространстве, давайте проделаем этот фокус. Еще одна мысль, которая приходит в голову, что у нас есть вот такое разложение, есть метрика здесь, значит, есть метрика здесь, и появляется какая-то метрика, и эрмитов. Возникает вопрос, это одно и то же или не одно и то же?
Видите, у нас на самом деле беда, потому что у нас комплексификация это не совсем правильно происходит.
Почему?
Ну, потому что у нас дирам, он действует на чем? На вещественном многообразии.
Да.
Вот. Но если мы комплексифицированное пространство вычисляем, а потом комплексифицируем, у нас получается не то же самое.
Ну, естественно.
Вот.
Да, нет,
мы его не комплексифицируем на самом деле, этого дирама.
Нет, еще раз, мы сначала овеществляем, потом у нас получается дирам. И потом мы его комплексифицируем. Получается комплексифицированный дирам.
Он действует не на том, что было изначально.
Да.
На комплексном пространстве в 2 раза больше размер.
Правильно. Вот, отсюда, смотрите, вот это вот комплексное пространство в 2 раза больше размерности, оно приводит к тому, что у нас вот эти вот, смотрите, у нас, x имела комплексную размерность n. А вот эта вот, штука, PQ, она имеет место для всех PQ, которые каждый по отдельности меньше либо равно n. То есть у нас, в частности, есть лямбда nn. И что это все изображает? Это изображает вот что. У нас здесь у нас стоит лямбда, только здесь, наверное, q касательно нужно. То есть здесь у нас стоит такое, да? И вот эта штука, она, как довольно-таки очевидно, имеет размерность 2n. Из-за того, что у нас разные комплексные структуры, одна была дана изначально, там потом еще возникает, там еще одна, возникает много путаницы. Вот мы сейчас, собственно, это наблюдаем. Давайте разберемся. Хорошо, давайте, let's have a break. And during the break, let's think a little and see if we can sort this out. And if we can't, let's just move on. And I'll try to write some notes and post them somewhere. Okay. Okay, let's have a break, 20 minutes. Okay. Well, the latest news is that there are well, there are two possible ways to introduce a Hermitian metric on each of these spaces. One is given by this isomorphism, and the other is given by this observation. These two methods may give the same result, or they may not. They might not. We don't know. But if one uses this this recipe, then as Leonid and Yegor say, this operator is okay. Let me write dc plus dc conjugate. So this operator is dc conjugate, where this conjugate is taken using this prescription. So basically, we take the the conjugate C. So this is dc plus dc conjugate, and this is d conjugate C. So the two operations commute. Okay. Well, if we believe this, then it's well, it's good news, because we all we need to do is to calculate the conjugate is to remember the conjugate that we already have and complexify it. Okay. Now, if this is true, then then we have this formula, where this is the complexification of the L conjugate. And now let's look at this formula. We have this decomposition into PQ components, which is orthogonal more or less by definition. That's how we constructed a metric on this space. Okay. Now, if I have an operator which takes PQ the PQ component to the P plus 1 Q component, then the conjugate will go in the opposite direction, and in particular the conjugate will take components to components. So it can't mix up several components. And then basically using this formula, we we see that d bar conjugate is just the vertical component of d conjugate, and delta conjugate is the horizontal component. Then basically this formula and the same formula for delta instead of delta bar is just this formula complexified and then evaluated on each PQ component. Does this make sense? I'm not saying let's forget whether or not it's true. Does it make sense? Does the statement make sense? То есть я утверждаю, что вот, значит, чтобы, то есть левая часть вот этой формулы, значит, это левая часть, значит, на комплексификации. То есть сейчас, да, значит, левая часть этой формулы это комплексификация, то есть левая часть вот этой формулы на PQ компоненте. Что это? Это, значит, это комплексификация левой части вот этой формулы, значит, но какая-то, то есть это какая-то компонента комплексификации левой части вот этой формулы. Логично для правой части. Почему? Потому что звездочка переводит, значит, звездочка с крышкой переводит PQ компоненту в n-p n-q компоненту. Вот, и компоненты не могут перемешиваться. Значит, ну давайте мы применим, да? Значит, у нас, значит, была PQ компонента, применили звездочку, получили какой-то, значит, еще n-p n-q компонент. Потом получили вот это. Значит, у нас, значит, применили вот это. У нас эта штука расползлась там из какой-то одной компоненты в две, значит, стоящие друг друга, значит, на расстоянии 2 по вертикали. Значит, ну, то же самое будет, если мы применим правую часть. Если мы применим все, то, значит, все, в смысле, значит, вот это вот, значит, вместо вот этого, то мы получим абсолютно то же самое, но, значит, вместо двух компонентов будет 4. То бишь, левая часть вот этого получается из левой части вот этого, значит, там, но там забыванием двух компонентов. So what I just said is that the left-hand side of this is the left-hand side of this with 2 of the 4 components forgotten. When we apply D to PQ form, we get something of something in degree P plus 1Q and something in degree PQ plus 1. And the same if we apply D bar, D conjugate. Except we have components of degree P minus 1 Q and PQ minus 1. So 4 components. Okay, now the star takes components to components. It doesn't mix components. No. So my claim is that this is the vertical part of this, and which is why the two commute. Okay, as I said, this is this part is a bit tricky. So I will try to write it all down and check everything. And in particular, all statements from linear algebra. Okay, now now we have three options. Option one is to see how this formula implies what we're after for vector bundles. Option 2 is to start talking about sublove spaces, and option 3 is the Chern character. I suggest we I'm personally in favor of either option 2 or option 3, because I'm tired of this topic. Basically, what one needs to do is to write it down properly, and then all formulas will hopefully become clear. And what do you think? Sobolev spaces and Saman, Yegor, and Volodya. Okay, well, let's talk. Let's talk a little about Sobolev spaces. Okay. Okay. Well, let's. Okay, let's see. So we want to introduce Okay, first the informal definition. It's the space of sections with all derivatives of order less than or equal s. Well, let me put an x here to well, to stress the fact that it's a space of sections of some type. So all derivatives of order less than or equal s should be in L2. This definition is, well, it's not really a definition. So let's give, but still the idea is there. Well, first of all, let's remember what the Fourier transform on Rn does. Let's see. To simplify the Fourier theory, we want to talk about functions with complex values. Although these functions needn't be holomorphic or even differentiable, they're just complex valued functions. Okay. Now, let's recall that the Fourier transform is given by this formula, where what I have in brackets is a metric, some Euclidean metric or on Rn. Now, if f is square integrable, then Then so is the Fourier transform, and the inverse is
На самом деле это немножко нечестно, потому что для функции z L2 оно может быть неопределено.
Сейчас, значит, что еще раз?
Ну, для функции z L2 преобразование Фурье бывает неопределено вот этой формулой.
Ну, вроде как всегда продолжить.
Ну там да, там надо в L1 брать и продолжать по непрерывности на самом деле.
Так, хорошо, да. Значит, действительно, значит, давайте честно. Значит, если функция принадлежит L1, то интеграл сходится. Значит, но это ничего не говорит насчет того, принадлежит ли функция L2. Okay, so let's be honest. Yes, so let's see. So the Fourier transform is an isomorphism of L2. But there are two things that could happen. For example, if we have a function in L2, it needn't be in L1, and vice versa. So, for example, well, the function 1 over x on 1 infinity is such that the integral of the square converges, but the integral of the function doesn't. And there are similar examples. By the way, can someone give me an example of a function which is integrable but not square integrable? Well, let's.
Maybe 1 over square root of x.
Yes, for example, x to minus 1/2 is inside L2 of 0, 1. Is inside L1 of 0, 1, but not L2. And well, if we extend both functions by 0, then we get the same statements for L2 and L1 of R. Okay, so
So clear that this Fourier transformation is always convergent, and maybe if I have the
well, it depends. For f which is integrable, yes. Although if f is inside L2 but not necessarily integrable, there is a way to define the Fourier transform by continuity.
For example, don't we need to assume
And-
like complexes supported or something?
Well, yes. By the way, one of the ways to prove that we have an isometry would be to consider the Fourier transform on Hermite polynomials. I think these are orthogonal polynomials which form a basis for L2 of R. And then basically on these polynomials one can calculate the Fourier transform directly. And then so proof. Well, it's one of the proofs. And by the way, well, I don't remember what the Hermite polynomials are, but it's one of the definitions is that we take just the monomials x, 1x, x squared, and so on, and then we use the scalar product with weight e to the minus x squared, and we apply the Gram-Schmidt procedure to this set of monomials, and then we get something, and the something is the something is the Hermite polynomials.
Are they orthogonal with some weight?
Yes, with weight e to the minus x squared on R, and then we just deduce Rn from R. Okay, so it's not a massively difficult theorem. But one needs to evaluate the transform on some polynomials. Okay, now. Now I want to define the Sobolev norm of a function from Rn to C. Let's assume that this function is such that let's assume that this function is such that the Fourier transform and the inverse of the Fourier transform is given by the formulas which are on the blackboard. For example, we could assume that the function is finite in the sense that the support of the function is finite. This will suffice for our purposes. And let's also assume that the function is smooth. Well, what does this mean? This means the Fourier transform. This is the modulus. With respect to the metric, and then and then I just integrate. The integral makes sense. Why? Well, because here I have f roof, and this is a function which belongs to the Schwartz space. It may not have finite support, but it belongs to the Schwartz space because let me add this statement here. The Schwartz space is the space of smooth functions which tend to zero faster than any that tend to zero when multiplied by any polynomial. Tend to zero when the norm of x goes to infinity. Okay, such as, for example, e to the minus x squared. Valeria, does this make any sense? Samam. Okay, so the Schwartz space. So this is inside the Schwartz space, so we needn't worry about whether or not the integral converges. Okay, and now we want to we want to extend this definition to sections of vector bundles. What do we do?
Does this norm satisfy right now inequality?
Well, because this norm is induced by a scalar product. Which scalar product? Well, basically, I take the scalar product on. I could use the scalar product on the Schwarz space, and then I apply the Fourier transform and take the scalar product in the Schwarz space given by this formula. And but this is not the only way to define the Sobolev space. For example, hold on. There's something missing from this formula. Can you tell me what? It's the square of the norm. Okay. Now there's an analog of this. Instead of 2, I could use a p, and then I would need to put a p here, and then I would get an LP analog of the Sobolev spaces, which is also useful, but it's the theory is more complicated. Let's just start with the L2 theory.
It is not induced from the scalar.
Well, obviously, on LP, the norm is not induced by any scalar product.
But I think something like Minkowski inequalities.
Yes, but there is a series of inequalities which have. So I remember the names. It's Holder, Minkowski, and Cauchy-Schwarz, and Bunyakovsky, and I keep forgetting which is which. Anyway, we still get a norm for an arbitrary p. We still get a norm, but not a scalar product. Okay, now we want to generalize this to sections of vector bundles. Okay, now for technical reasons, I will now consider complex vector bundles. Yes, they're complete because that's how we are going to define them. We take the space of smooth sections and then complete it with respect to some metric. Now I will define this this metric. Well, the metric will be induced by some norm. So I will define the norm. Yes, let's see. Okay, suppose I have a section of I don't know. I have a section of E. I want to I will explain what I will write something and then I'll explain it. Okay. Okay. Now, what is alpha? Well, alpha is the index in some partition of unity. Now, do the words partition of unity make any sense? Okay, so we take some partition of unity and we moreover we okay, I'll write it again. We want to have a partition of unity such that it is subordinate to an open cover such that E is trivial over each element of the cover. Now, once I have such a partition of unity, I could view phi times psi I as a collection of functions. Why? Well, because I can trivialize the bundle over U alpha, and this trivialization transforms a section with support in U alpha into a just collection of functions. Well, I know how to, and these will be functions from U alpha to C. Why to C? Well, because I have a complex vector bundle. Now, for each individual function, I know how to define the L2 norm, the Sobolev norm. And then, well, then if I have a collection of functions f1, etc., I don't know, fr, then I take just the then I just take the L2 sum of the norms for individual functions. In other words, I take the squares of the norms of the components, and then I declare that the norm of the vector, the squared, is the sum of squares. Okay, so this allows me to define this, and then I take the sum overall alpha in whichever set the index runs through. Okay, now does this make any sense?
It's not clear that it is dependent on choice of new alpha and choice of partition of unity.
Yes, and trivializations as well. We need to choose those. Well, it's not clear. It's not clear at all, but it's plausible.
It's true.
Yes, and it is true that the resulting since we assume that X is compact, it is true that the resulting norms on the space of smooth sections are equivalent. So when we take the completion, the spaces will be isomorphic, although not identically the same.
With all norms on infinity sections of compact manifold.
No. All norms, meaning all norms we obtain in this way, by taking an open cover, trivializing, and then using this recipe for the Sobolev norms of the trivialized function. Obviously, not all norms on it's a vector space. Not all norms are equivalent. It's an infinite dimensional vector space, so not all norms are equivalent. Okay, so the claim is we made some choices when we constructed the space, but none of those affect the. But any two choices will give isomorphic spaces WS, and moreover there is a preferred isomorphism between any two spaces. So from now on we'll just say WS without mentioning the choices. Now, does this definition make any sense? does the word completion make any sense? Okay, let me say another thing with let me say another thing which is important, and I forgot to mention it earlier, but let's mention it now. Here I define the Sobolev norm for Schwartz functions on Rn, but there is another way to define an equivalent norm. Let's mention it. So this time I take S to be integer. In this definition, S could be any real number. Now for integer S, I could take the following thing. I could take all derivatives of order less than or equal S, and take the L2 norms squared of those derivatives. What's the result? Well, the result is some number which makes sense because we assume that function is in the Schwartz space. Okay, now this norm okay, maybe I'll okay, I'm using the same symbol for two different norms, but these norms are equivalent. So it's bad, but it's not too bad. And how to prove that the norms are equivalent? Well, we use the fact that the Fourier transforms derivatives into multiplication by polynomials. Does this make any sense? Or do I need to recall what this means. Okay, so let's again assume that the function is inside the Schwartz space, so we don't need to worry about whether or not some or another integral converges. Okay, so okay, and there is so okay. Hold on, I'll write alpha upstairs. Let's see, what is roof? Roof is the Fourier transform. What is d alpha? Well, it is the same as d by dx alpha. Some combination of the partial derivatives, some composition of the partial derivatives. Okay, now this composition of the partial derivatives is again a Schwartz function, so it makes sense to write this. Now this is a function of psi. Well, let's recall that okay, well, this is a function of psi, so my claim is that we have this formula, but there is something here, some multiple of I. I don't remember. So it's either alpha or minus alpha. Is there anyone who remembers the experiment here? Anyway, so up to multiplication by I to the something, the Fourier transform of the derivative is the same as the Fourier transform of the function times some monomial. Which monomial? Well, the same as well, it's basically the monomial with the same multi-index as the derivative. For example, if we take d by dx instead of this d, then here we multiply by x, and so on. And so okay, well, plus or minus. Anyway, okay, so using this observation, it's not very difficult to prove that these two norms are equivalent. Two norms on the Schwartz space. Okay, now let's see. So we have defined lots of Sobolev spaces, basically for every real S. Although we will mainly be interested in the Sobolev spaces which correspond to the integral values of S. Okay, well, first of all, let's notice the following thing. Suppose we have S less than T, then W then one of the two spaces is included in the other. Now, let's see, which one's which? Well, let's look at this interpretation. If the first, for example, two derivatives are L2 integrable, then the zeroth and the first derivatives are L2 integrable. So we have this inclusion. The larger the value of S, the more derivatives should be L2 integrable. Okay, now well, let's also look at this formula. Suppose we have S less than T. Then the denominator here will be larger for T than for S. And so if the integral for T converges, so does the integral for S. Does this make any sense? Well, actually, well, for one should be careful. For functions in the Schwartz space, all integrals converge. But still, the integral for T will be larger than larger or equal than the integral for S. And so this if we start with the Schwartz functions on Rn, we have this norm which is greater than or equal than this norm. So the inclusion is continuous. And while we're at it, let's state the relic lemma. Well, let's
T is more than S.
yes. If t is more than s,
And this integral is more for S.
uh,
Denominator for less S, denominator is bigger.
okay. Well, let's check it. So t is less than t is maybe you're right, but let's check it. So if t is less if t is greater than s, then minus t, sorry, minus s is greater than minus t, and so okay, so 1 plus psi minus t, and greater than or equal in the exceptional case when this is 0. Okay, so the yes, the integral for yes, you're right. So the integral for s is greater than the integral for t. So if the integral for s is small, the integral for t is also small, which shows that this the identity inclusion of the Schwartz functions induces a continuous inclusion of the completions. And then we have the same inclusion for sections of the vector bundles. But the philosophy is this: if the greater s is, the more derivatives are L2 integrable.
The more S, the more the norm. So the norm on left space is bigger than the norm on right space.
Yes. So we want to show that this map is continuous. So if
How do we get this map?
if this norm is small, this norm is even smaller.
Yes.
So okay, let's think.
Кажется, как раз делить. Насколько я понимаю, там принцип, что если увидеть производные функции, возьмем там большую производную r, применим к ней иксов числители, и они как бы сократятся с тем, что есть знаменатель.
Сейчас, давайте вот на эту штуку посмотрим. Значит, вот эта штука, значит, чем больше, чем больше, чем больше s, правильно? Ну, потому что нам просто больше всего откладываем.
А вот это тоже работает.
Значит, теперь давайте посмотрим сюда. У нас что? У нас значит, s больше t.
Норма s больше, чем норма t.
Здесь не работает, по-моему, да.
Сейчас, значит, вот.
Норма s больше нормы t. Это все нормально.
Сейчас, значит, вот у нас s, значит, s меньше t, тогда, да, тогда здесь тогда получается действительно неравенство в неправильную сторону.
Там прямиком надо ударять просто.
Сейчас, ну сейчас, подождите, значит, так.
Я посмотрел. Признаюсь.
Так, ну, так, хорошо, значит, ну, да, сейчас давайте еще раз внимательно посмотрим. Значит, нам нужно, чтобы вот эта норма была больше. Вот, соответственно, нам нужно неравенство вот в эту сторону. Ну, хорошо, давайте умножим дурацкое дело нехитрое. Yes, okay, so yes, the norm, so if s is less than t, then the norm for t should be greater than the norm for s, as is suggested by this equivalent norm. Okay, so the formula I wrote here was completely wrong. But on the other hand, if we replace s by minus s, there is some chance. Okay, so and then we do get this inclusion. Because if the norm for t is small, then the norm for s is also small, so we get at least a continuous inclusion. Now I would like to state one result, which is very important. Значит, сейчас кси в квадрате.
Просто я как рассуждаю. Ну, да, мы хотим понять, что вот эта норма эквивалентна той, так более-менее. Вот хотим посчитать норму d альфа от f, L2 норма. Но можно считать норму преобразования Фурье, так это изометрия. Тогда L2 норма d альфа f, это что? Это L2 норма преобразования Фурье от d альфа f. То есть L2 норма от кси альфа на f с крышечкой.
Да, ну логично.
И когда мы вот там квадрат, дальше мы считаем, вот квадрат будем считать норму, да?
Ну хорошо, да.
Там мы считаем кси в степени альфа в квадрате.
Так, хорошо, да. Я значит, согласен. Значит, сейчас давайте еще раз значит, подумаем внимательно. Давайте положим s равно единице. Let's take s equal 1. Then, well, if what I need to, the condition I have on f is that the first derivative is square integrable. Here after I take the first derivative, I get some variable, just one. But then I take the square, and then no.
I think I can say denominator is one plus absolute value of psi squared to the power s is more than psi to the power alpha squared. Multiplied by some constant c.
Okay.
This norm is more than c.
Okay, I think we've run over time, and anyway, this is this thing is I'll just look it up for the next time. It's not very difficult, but let's just assume that we have the right formula. Then there's this statement which we will use when we prove the elliptic when we prove the theorems about elliptic operators, which we stated a while ago. Now the inclusion of Wt inside Ws is a compact operator. Now does the phrase compact operator make any sense? This means both are normed spaces. And an operator is compact. From one normed space to another, if and only if the image of the unit ball has a compact closure. And this this condition implies in particular that the operator is continuous, but it's much stronger than just being continuous. Okay, so as I said, we've run over time. Let's stop here and continue next time. Next time, I will try to prove this lemma and another lemma, which is called the Sobolev lemma, and which is also quite useful. And the Sobolev lemma says that actually, if I fix the dimension of the ambient space and take S large enough, then then all elements of WS will in fact be not just square integrable, but continuous and continuously differentiable. Okay, are there any questions? Да, единичный шар, вообще говоря, не компактный. Ну, и, не совсем компактным, но с компактным замыканием. То бишь очень, ну, в общем, в каком смысле вот пространство WT очень маленькое, то есть оно не просто лежит, оно там значит, лежит и значит, где-то скрывается в уголке. Так, ну хорошо, давайте, да, значит, давайте тогда скажем, что на сегодня все, хорошо, понемножку, и я пришлю, значит, email про голосование.